Hello again. Today's focus will be on external line boundaries. We'll first look at all the different kinds of line boundaries that are available in Anaqsim, and with the focus being on external line boundaries, we'll talk about line sync elements, which are what are used for all of the external line boundaries. And we'll talk about the extent of a domain and how that is defined in Anaqsim through the use of external line boundaries and the algorithm that's employed there. Talk about boundary condition equations for each kind of external line boundary, how you specify them, and we'll also look at how you can check their accuracy. And the last topic there, some of these external line boundaries require a left and right sense, and I'll go through the standard for that, which is just arbitrarily chosen. This table lists the kinds of line boundaries that are available in Anaqsim, and they are listed as either internal or external. External ones here form the external boundaries of domains, and the first three also are the external limits of the modeled area. Interdomain boundaries form the external boundaries of domains, but are internal, not on the outermost edge of the modeled area. So head specified is just what you think it is, where you specify the head. Normal flux specified, you specify the normal component of aquifer discharge, which is specific discharge times saturated thickness. The head-dependent normal flux is also known as a third type boundary condition, and that's where you have a normal component of discharge that is proportional to the difference in head between the modeled head at the boundary and some head that you've specified. So for that, you specify head and a conductance factor. Interdomain boundaries are where the domains can abut. These can be one-to-one or one-to-many if you're going from a far-field single-layer area to a multi-layer area. The kinds of elements that are employed for all of the external line boundaries are line syncs, where it's basically a well element integrated along a line. And there are other line element types, line doublets and line dipoles, which have zero net discharge and are the integration of a dipole along a line. We'll talk about that more in an upcoming session. Here are a couple of plots showing contours of potential or head and contours of the stream function for line sync elements. And line syncs are extracting water here along a line segment. So the one on the left is the simplest kind of line sync, where the rate of discharge is consistent along the whole length of the line sync element, which is shown in black here. And you can tell that it has a consistent rate of extraction along its length because the spacing between these stream function contours, which are blue, is consistent all along its length. And the solution here, and for the one on the right, line sync solutions in general, are solutions of the Laplace equation. So the stream function and the potential contours form flow nets, which you can see obviously here in both pictures. We've got nice looking flow nets. On the right side, the discharge per length varies along the length of the line sync element, which goes from here where the cursor is over to here. And you can see at this end of things, the spacing between adjacent stream function contours is quite small, which means it's a high rate of discharge here compared to out here where they're more widely spaced. The blue are stream function contours, the red are potential in this plot. Another thing to note is that the potential and the head are continuous across a line sync. So the dotted potential or head contours here, or the red contours here, are continuous from one side to the other. But there is a jump in the stream function which must occur whenever there's extraction from the aquifer. And because there's a net extraction, that jump in the stream function extends off towards infinity in one direction or another. Here's the end of the line sink, but this thing called a branch cut, which is a discontinuity in the stream function, continues off to infinity. Same thing occurs in this plot, going to the left of the line sink. With line elements, one of the input variables that the user selects is called parameters per line, and that is the number of unknown strength parameters per line segment in a line boundary. And if you have higher numbers for that parameters per line, that means that for a line sink, the rate of extraction can vary in a more wiggly manner along the length of the element. And this plot down here shows 3 different parameter per line distributions of discharge per length along the length of a line element. Let's just say it goes from -1 to +1. So the simplest one would be a constant strength all along the length of the element. That would be in blue, where there's only one unknown, which is the discharge per length that's applied everywhere. And you can see that it is flat like that. You could increase that to 2 parameters per line, the green line, and then you'd get a linear variation from a higher rate at the left end of this element to a lower rate at the right, and varying linearly in between. And then go one step further to 3 parameters per line, the red curve, and then you get a parabolic distribution. And you can go in Anaqsim up to 10, I believe, 10 or 12 with the parameters per line. I find that most often I'm using somewhere around 2 to 6 parameters per line, depending on the situation. The properties of any domain are defined in the domain input, which doesn't say anything about where that domain is located. It gives the conductivities, the elevations, and that kind of information. The extent of a domain is determined by the external line boundaries that reference that particular domain that belong to it. And here's a plot that shows an example of a single layer model with 3 different domains, 3 different colors, and they are bounded by external line boundaries of various sorts. So for the purple domain, we have an interdomain boundary between it and the yellow domain here. We have a normal flux specified boundary here, the yellow one, a head specified segment in red, and another normal flux specified segment in black. For the green domain, it has one external line boundary, and that's a closed polygon interdomain that separates it from the yellow, and so on. This explains the algorithm used to define the extent of domains in Anaqsim. And it's something that is essential to know whether a certain XY location is inside one domain or another. So the algorithm goes like this. Consider point A. If you work to the right in the positive X direction until you're outside this blue domain, you have to cross one external line boundary right there. At point B, if you go to the right, positive X direction, you cross 1, 2, 3 places where you cross an external line boundary. It turns out that a good algorithm is to make use of this fact that if you're inside the domain, there will be an odd number of crossings between where you are and far away, say infinity. And I just use in the algorithm going in the positive X direction, how many crossings are there of these external line boundary segments? And you count them up, and if it's odd, you know that your point is inside the boundary. If it's even, you know you're not. Consider a point over here where the cursor is. There are 2 crossings to the right. That's an even number. I'm not inside the domain. Consider a spot here. There are 0 crossings to the right. It's an even number. I'm not in the domain. So to make this work well, the coordinates where line boundaries meet must match exactly. For example, if you have a gap like I've shown here, then this algorithm breaks down. If I'm at a point right here, because of the gap, there is no crossing to the right of me, and Anaqsim thinks I'm outside of this domain. And again, if I go over here, Anaqsim thinks I'm inside the domain because there's only 1 crossing. So luckily, Anaqsim has a snap to feature in its digitizing so that you can snap to existing element coordinates when you're doing a string of different external line boundaries to define a domain. This will lock them exactly at the right coordinates. In the input for various line boundaries in Anaqsim, you typically specify a value at the beginning of a polyline that forms the line boundary and at the end, the starting and the end points. And this could be, for example, the heads that you're specifying at a head specified line boundary, or the normal component of discharge for a normal flux specified line boundary. So the algorithm works this way. You first specify the values that are in the input table at the start and the end of the polyline. Those would be these blue values. Let's say this is a head specified line boundary with 2 segments, and the starting head is 93 here. The ending head is 95 there. That's what you've put into the input. The intermediate vertexes are interpolated just based on numbers of vertexes. So here we only have 1 intermediate vertex, so it's going to be halfway between the starting and the ending heads. So we assign that this green value 94. Then within each segment, the heads are interpolated linearly from 93 to 94 here. In this case, there are 3 control points. We have 3 parameters per line. And using linear interpolation, these black values are assigned at those red control point locations. The location of control points is not just algebraically spread evenly across a segment. A cosine function is used that concentrates more densely spaced control points near the tips of the elements and more widely spaced in the middle, which is where the effort is needed more near vertex intersections. Let's talk about head-specified line boundaries and how those specified heads get applied. You basically determine a number of control points based on your parameters per line. Say if it's 4 parameters per line, these little X's would be the 4 control point locations for this line segment. And each line segment in the polyline gets 4 control points. Here's the same thing, but where we've selected 8 parameters per line. And you can see that the control points, these green X's, are more widely spaced in the middle of the element, more closely spaced near the vertexes at the ends of the elements. The equation that gets applied is simply that the simulated head equals the specified head at control point locations. So you achieve the interpolated specified head exactly at each control point with this kind of line boundary. With all line elements that have unknowns in them, you can check the accuracy of the boundary condition that you've achieved compared to what you've specified. And for a head specified line boundary, you get plots that look like these two. The red lines are the head you've specified, and the blue curve is what you've actually achieved with the model. This left-hand plot has 4 parameters per line, so 4 control points, And you can see there are 4 places where the modeled head is exactly what was specified, 104, these 4 spots. And it deviates in between, it's approximate in between, but you can see by the scale, we're talking very tiny deviations from what was specified. And you can increase the accuracy of your boundary condition representation by going to more parameters per line. The other way to do that is to break your boundary into more line segments, which packs more control points in than longer line segments. And I typically, like I said, use somewhere between 2 and 6 parameters per line, 2 to 4 most commonly, and then adjust my vertex spacing to achieve a reasonable level of accuracy. You can see from this plot that this one with 8 parameters per line has 8 locations where the specified head is met perfectly. And in between, the deviations are now smaller than they were over here with only 4 parameters per line. But again, both of them are doing a nice job of approximating that condition. There's a nice feature in Anaqsim where you can specify an outer boundary that is circular, roughly circular, to be head specified and with a specified gradient. And it's quite simple, one line of input, and it sets your far field up, which can be useful in many cases. So it creates a circular polygon of external head specified line boundary elements, this green roughly circular polygon, and the only input you need to do here are these 4 items here: the center coordinates of the circle, the radius of the circle, the hydraulic gradient and its magnitude and direction, and the parameters per line for each of these segments. This plot here, by the way, is 2 parameters per line. And it sets up a cross flow, basically. And you could set that far away from your model if, for example, you wanted to just simulate a pumping test here, or a dewatering system in the middle, or a remediation scheme, or mounding due to a leaching field, or something like that. And it is quite useful and super quick and easy to do. This illustrates how boundary conditions are set up for normal flux specified boundaries. The interpolated normal flux is met over 4 subsegments of each line segment, not at control points, but over subsegments. And the total discharge here over this subsegment is Q1, and that matches the specified discharge over that same segment. Likewise, Q2 achieved in the model equals the specified discharge over this segment. And these segments again are arrayed using a cosine function that makes them a little wider in the middle of an element and shorter near the ends of an element. In this particular case, there are 4 parameters per line, so there are 4 different discharges that must match when the model solves properly. Because a line sink has different components, directions of discharge coming in from left and right, it's important for this kind of boundary condition to have a convention for the way the order of the vertexes in the element. And the convention that's adopted here is that for an external line boundary, the vertexes must go counterclockwise around the domain. And that way, the actual domain is to the left of the line boundary as you walk along it from, say, the first vertex towards the last. And that's just a convention that has to be adopted. When you check the accuracy of a normal flux specified boundary condition, you get plots like these for each line segment, or for one line segment, let's say. In this plot, we've got a model with 4 parameters per line for this boundary. And again, the normal discharge is being met perfectly over 4 sub-intervals here. One that goes from the right end here to maybe about here. And you can see that it only perfectly matches at one spot within there, but the net discharge does match perfectly. And that's true for 4 segments from left to right, even though at any one spot, the match of the normal component of discharge to what's specified isn't perfect. It is perfect over sub-intervals. And when you up the parameters per line to 8, you can see that the match tightens up even more, although either of these is probably, the difference between these two models is probably negligible in terms of the patterns of flow that you would get. The boundary conditions at a head-dependent normal flux or third type boundary are described here. The user specifies 2 things, an external head H star and a conductance K star over B. And this illustration will help us understand what those things are. If this is your domain, this blue area, and this is the external line boundary, there's it's useful to think of a fictional domain that lies outside of that, this orange area, and the distance from the actual boundary to a fictional boundary normal to that is B, and you assume that this head H star applies at that distance B from the actual boundary. And then Darcy's law is used to compute the discharge that would result coming from this orange area through the domain boundary here. And that's based on the head difference, and actually it uses potentials. It computes a specified potential out here based on your inputs, and it knows a potential here, and it computes the flux, which is the gradient of the potential from here to here. And that flux is what goes through the model boundary right there. And the condition that I've just described is applied at the control points in your line segment. So for example, if you have n of 4, there would be 4 control points, these green X's here. When you check the accuracy of a head-dependent normal flux boundary, Anaqsim computes 2 things, the modeled normal flux and a normal flux computed based on the specified conductance, the specified head, and the modeled head at the boundary itself. That would be the blue curve in this plot. The modeled normal component of discharge is the orange curve. And in this plot, there are 4 parameters per line, so it gets it exactly at these points, 1, 2, 3, 4, and approximately in between. And then with 8 parameters per line, you get it exactly at 8 points and a closer approximate distribution in between. Here are the boundary conditions that apply at an interdomain boundary segment where you've got domains on either side, possibly multiple domains on one side. The first condition is continuity of discharge, which sets the discharge on the plus or left side equal to the discharge on the minus or right side of this over subsegments. In this case, in this illustration, there are 4 subsegments because we've got 4 parameters per line segment here. So these black dotted lines show the division of those 4 subsegments, and the discharge coming in on this side of the boundary must equal the discharge coming out on the opposite side of the boundary. So Q1 minus equals Q1 plus, and so on for all 4 of these subsegments. That's one condition. The other is continuity of head, at the control points that are these green X's, which are in the middle of the subsegments. So the head on this side equals the head on that side. And if you have multiple domains on one side, then the head in all domains is equal. So let's say you had 3 domains on the side I'm on here, above the green line, and only 1 domain down here. The head in all 4 domains would match at this control point and at the other 3. Which means when you go from a single layer to a multi-layer area, right at the boundary there are no vertical gradients because you force the heads to be all equal in the multi-level side. When you check the accuracy of inter-domain boundaries, you get 2 plots. The first is a check of the head continuity, and it plots the head along the line segment for all domains present at this inter-domain boundary. In this case, there are only 2 domains present, and the 2 curves pretty much fall on top of each other with 4 parameters per line and for 8 parameters per line. There's not a lot of difference or daylight between these curves. The other plot that gets generated when checking inter-domain boundaries is a plot of the normal component of discharge across the boundary in not every domain. If you've got a multi-level area, those multi-level ones are lumped together and compared to the single level on the opposite side. So it's a comparison of domains to the left and to the right of the boundary. And what is met is the discharge over intervals, in this case with 4 parameters per line. There are 4 sub-intervals here, like one that goes where I'm showing here near the end, a broader one that goes to the middle of the element, another broad one, and then another short one near the end of the element. And you can see that it matches not perfectly at every point, but it does match perfectly for each of the 4 subsegments. And here you can increase the accuracy with 8 parameters per line. And again, you get a little bit tighter fit of these 2 curves. We've talked a bit about the left and right sides of some of these external line boundaries, and it is important with these 3 kinds: interdomain, normal flux specified, head dependent normal flux. It doesn't matter for a head specified line boundary, it turns out. But for these, you do have to know whether the domain is to the left or to the right. And the convention that Anaqsim adopts is illustrated here. Let's look at this set of x, y coordinate pairs for this 4 vertex line boundary here. The first pair, or first point, is point 1 here, and the second, third, and fourth here in the order of coordinates. So the left side of this boundary would be to the left as you proceed from the first vertex towards the last. Imagine yourself walking on this boundary. The domain that's to the left would be to your left. The domain to your right would be the one to the right. So that's the convention. I forgot to mention in the previous slide that for several kinds of external line boundaries, normal flux specified, head dependent normal flux, the domain must be to your left, and you go counterclockwise around the exterior boundary of a domain. For interdomain boundaries here, it does not matter whether you go clockwise or counterclockwise. All that matters is that you understand the convention for determining left and right. In this case, it's a closed polygon that starts here, the first vertex, second, third, and so on around to the last vertex. So using our convention, the interior of this polygon is to the left, and in the input you would put the domains to the left, would be the interior ones, and the domains to the right would be the exterior ones.